Excuse me. Hi, welcome to chapter 2. Um, I'm going to do 2-1 and 2-2 together on this one. They're both relatively short. 2-1, we're going to use pieces of this throughout the semester, and then some pieces we'll never look at again. Um, Basically, the pieces that talk about where our derivatives come from, this is the theory behind it. We don't need to worry about that as much as we go for this class. Hang on a sec. Basically, if you're interested in the proofs of how these things work, we can dive into that. Most of the time, people just tell me they want to know how it works, and that's enough. So, excuse me, our derivatives, which is the first half of this term, and the second half will be doing the antiderivative or integrals. Your derivatives measure slope, rate of change. So if we look at a simple parabola here, this guy, and we want to figure out how is my graph changing at a particular point, we would find the tangent line, or we'd find the derivative. So, oh, sorry, my cat is singing the song of his people this morning because it's morning. So if I want the slope of the line here, I would really I just pick a line or a point on the line and draw a tangent line. It's a line that touches our graph there. We're going to dig into those a little more as we go. So a couple reminders. If we want the slope of a line given 2 points, x1, y1, and x2, y2, our slope, our m value, is y1 minus y2 over x1 minus x2. Or in calculus, we're going to use delta. So delta y over delta x means the change in y divided by the change in x, your rise over run. So the triangle is delta, it means change. That is going to be a common thing we see. You will see delta x over and over and over again. So just wanted to introduce that early on. Another important thing we need is the equation of a line. Hopefully this is familiar to you. If not, we need to talk. But we'll be given, or we'll find a slope, we'll be given a point, and we plug it in and get the equation. Most of the time we want to put it in y equals mx plus b format. So once we get our data, move it around, simplify it, make it look nice. But I like this version of the equation. Your x and y stay x and y. Your x1, y1 turn into numbers, as does your m. Just because you don't have to think, okay, what do I have to substitute back in? No, once you plug it in, it's done. Clean it up. It's my favorite way to go. All righty. The big thing for this section is the difference quotient, or the slope of our line. So I gave you a slope formula up here, y2 or y1 minus y2. Sorry, you can do it either way. Over x1 minus x2. That's what this is saying. So this acts like our y1. This is our y2. And change in x is just, oh, come on, pen. Hang on, my pen is, oh, there it goes. x1 minus x2. That's all this is saying, is we're taking 2 points and seeing how they differ. For us, we've dealt with difference quotient in like pre-calc and some of our algebra classes. So now we want to see the limit as x goes to 0. So if we take 2 points on our line, and one of them we're going to lock in, graph here. So say we want the slope at this point. We're going to pick, this point is locked, so it does not move. I should use something that's not an x. L for lock. And then we're going to pick points that are really close to it and find them go closer and closer and closer. And eventually that'll give us the slope there. So we don't deal with secant lines in here, but that's really what we're looking at. So what's the slope between these 2 points? Get closer, what's the slope here? What's the slope here, etc. Eventually, as the limit between our points goes to 0, we'll get the slope at that particular point. Okay, so I'm going to use the difference quotient above to find the slope of, actually, I'm just going to find the line. So find the tangent line. First thing I'm going to do, we need a slope. We have a point, we need a slope. So I'm going to say limit as delta x approaches 0. We've done limits last section. So now I'm going to plug in -2 for x for, actually, how am I going to do this? Sorry, brain. I don't, okay, I never do derivatives like this, I'm sorry. Let's do it like this. You can plug in your numbers, but that is not my favorite way to do these. Not f of x. I'll plug in when I'm done. So all I did was every place I saw my x, I plugged in for the first part, x plus delta x. The second one stays the same, and then we have delta x on the denominator. And this right here is why you need a firm algebra base for calculus. Slope is easy. This we're about to do is kind of tough, harder. All right. I am going to write this out. I don't usually. This is my side work. Side work is usually in a different color. All right, so I take my first terms. It's going to give me x squared. My inner terms. This is weird. There's a couple ways you can write it. I'm going to write it as x parentheses delta x. My outer terms, we're going to get the same thing. And finally, my last, again, this is a weird one to write, so I'm just going to write delta x squared. Parentheses are your friend. Okay, so that was the first part, minus x squared all over delta x. I did not give myself much space, but that's okay. We'll make it work. All right, combine like terms. You'll notice that those two are the same. What I get left with is x times delta x, two of those. So I'm going to say 2x delta x. And this guy over here plus delta x squared all over delta x. Okay. Our goal is to get that delta x out of the denominator because that's what is mucking us up. So I have 1 on the denominator. Each term has 1. I can cancel 1 of each out. I'll show you another trick in a moment if you don't like delta x's. What am I left with? 2x plus delta x. No longer in the denominator, we don't care. So the limit as x approaches 0, or excuse me, delta x approaches 0. So this dude goes to 0. We just get 2x. So that's our slope. I'm going to put a box on it. Once I get here, I have a slope and I have a point. So we want to figure out our slope at that point. This says to plug in 2. So, or excuse me, plug in -2. So my slope I'm going to use, let's bring this down here in blue. Two times -2, which is -4. Now I have a slope and a point. Y minus my y1 is 4 equals my slope, which we found is -4, x minus -2. Be careful of your signs. Let's clean up the right side a little bit first. Gives me -4. +2 times -4 is a -8. This is weird. Add 4 to both sides. Sorry, my math is bad looking today. I get -4x minus 4. If I skip too many steps, please pause and scribble that out yourself so you can see where it's coming from. But that's the slope of our tangent line. Pretty straightforward. Well, semi-straightforward. The big thing, if you don't like delta x, because it looks really weird in your equations, it's kind of confusing sometimes, it's sometimes common to use h instead. So then our difference quotient gives me limit as h approaches 0. Ooh, f of x plus h minus f of x all over h. If you prefer that, because the delta x gets a little confusing, please feel free to use that. It's common. The book uses delta x, so I was going to use it too. But that's a valid way to deal with it. Okay. Let's just find the derivative. It's the only thing I can find. I didn't give a point here. So we're going to find the derivative. So limit delta x approaches 0. Take this and plug in x plus delta x. Parentheses are your friend. X plus delta x plus 4 minus parentheses again. It is so easy to get lost in the signs. So overdo parentheses if you need to. Okay. All right. I will FOIL. I'm not going to use as many steps written out as I did last time. I'm hopeful that we're getting better at those if we weren't good already. So distribute, I get negative 2x minus 2 delta x. I don't distribute to the 4 because it's not with the parentheses. Distribute my negative sign. I'm sorry if I talk too fast. I get excited because math is fun. Okay. If you do this right, you should be able to cancel off anything on top that doesn't have a delta x. Hey, look at that. So squeeze it in here in blue. I get limit as delta x goes to 0. What's left? Negative 2 delta x all over delta x. Sound effects help. And I get a negative 2. So that's my limit. That's my slope. Oh, that's great. Okay. So what we've done, which I believe I said multiple times, is finding the derivative. So our common notation for that is we get dy over dx, which is change in y over change in x. We can write d over dx of f of x. We get y prime, f prime, the little dot or apostrophe means prime, or dx parentheses y. Common notations. You'll get used to seeing them over and over again. I'd say the most common I use would be the f of x, y prime if I'm feeling lazy. This tells you what to do, so I don't use those in notation as much. Sometimes for differential equations, I'll use this one, but we don't have to worry about that too much. That guy's my favorite. I really don't use that one. So just FYI. Okay, this is a gross one. 2.2 tells you how to deal with these much simpler. I will say nothing if you decide to do 2.2 notes before you do the homework and use the methods from there to solve these. Honestly, I would consider it. It's a little bit more straightforward, a little easier. Okay, and I say this because I look at this problem and realize I don't want to do this method because it's yucky, but we're going to do it anyway. Once you learn the 2 and after methods, you're never going to look back. All right. Every place I see x, I plug in x plus delta x. So I get 3 times x. You know what? We're going to use h this time. And then we'll switch it back. H squared minus 2 x plus h minus 3x squared minus 2x all over h. I did not want to write delta x that many times, so h is a little simpler. Okay, I'm going to FOIL this in my head. We get x squared plus 2xh plus h squared. Distribute minus 2x minus 2h. Distribute again. Minus 3x squared plus 2x all over h. And again, if you don't see where some of this is coming from, pause and work out the details. I'm assuming most of us can either follow it or pause and figure it out. So I can work on that. All right. I'm going to be a little lazy here. Those two cancel. If I distribute my 3, those are going to cancel. So I just didn't want to write an extra step for that. I do distribute my 3 a little more. I get 6xh plus 3h squared minus 2h all over h. If I were to factor out an h, what am I left with? I get 6x minus 2, which is what I knew it should be. So that's our derivative. This is 6x minus 2. All right, I added this one because these are sometimes a little scary to deal with when you have a fraction. There's a trick. There's always a trick. All right, I'm going to use h again. Okay. Mobius. So I'm just going to write this out. Okay. This looks a little scary, and it is at first. The big thing I'm going to do is get a common denominator and get rid of that h on the bottom. So on the top, I'm going to multiply this guy by x plus h. Yes, thank you, sir. Uh-huh. They don't care about your opinion. Yeah, I know. Mobius has opinions on math today. All right. So I'm getting a common denominator. The quickest way to do that is multiply each one by the other's denominator. I don't care about the h on the very bottom. It'll work itself out in a moment, and I'll show you why. Oh, hang on. Cat's being bad. Yeah. Anybody want to borrow a cat today? He is being a cat. Okay, so on top, get down. 2x over x times x plus h minus, I'm going to distribute this because I know I'm going to need that, 2x plus 2h over x times x plus h. Oh, I tried to write a 4. There we go, saved it. All over h. You're making it really hard to write, Moby. Okay, bring my stuff together on top. I'm going to be a little bit lazy and distribute this. So I get a negative 2x minus 2h. And then this numerator would be a 2x. Combine like terms. My pink back. I get negative 2h over x times x plus h all over h. That's gross. Okay. So when we divide by something that's multiplying by its fraction, so this turns into 2 over 8, or negative 2h, wow. x times x plus h times 1 over h. That's much nicer. So now our goal is always to get rid of that h in the denominator. Boom, we have. Now if we plug in a 0, it doesn't matter. It's not going to hurt us. So I'll write this out formally. One last step. Gives me -2 over x times x plus h. I could have distributed the x, but it's not going to help us. It's not going to hurt us. It's just there. So if I plug in a 0 for h, I get -2 over x squared. And that's our derivative. So that's a common method, is getting common denominators and then simplifying. The biggest thing to remember is don't lose your h as you go. I can't count how many times I lost my h and the problem didn't make sense and it kind of blew up on me. So be meticulous, write down lots of steps. I know it's tedious, but in the long run, you'll get them right more often if you do that. Okay, we're going to use the previous problem for this one. It's like I thought ahead. Bring this up a little. Okay. Oh, no, I don't need that. Go away. We want to find the equation of the tangent line of the previous function at 2, 1. So I need my slope. So my slope, I'm going to plug in 2 where I see x. So I get -2 times +2 squared, -2 over 4, which is -1/2. Cool, almost there. Y minus my y1, I take my original point, which is 1, equals my slope, -1/2, x minus my original x value, which is 2. Little side work fraction. Nope, sit. All right. Negative times a negative is a positive over a positive, which gives me a lovely +1. So y minus 1 equals -1/2 x plus 1. Add 1 to both sides. Let's go this way. Y equals -1/2 x plus 2. That is the slope of our tangent line. So if we were to graph this, our line, that would be the line that touches at 2, 1. Cool. Okay. One final note out. Sit. Thank you. Our function is only differentiable at a place if it's continuous and the left limit and right limit agree. We talked about left and right limits last time or the time before. So most of our functions in this class, we're not going to worry about it because they're going to be continuous and the left and right limits agree. We won't have to worry about that. An example of one that's continuous and the limits don't agree is our absolute value function. It is not differentiable here because as we come down in this direction, our limit is, actually they do agree, don't they? Hang on, brain. Oh, our slope here is negative, it's positive. We just have a corner point, so corner point. Sorry. That's not true. Go away, bye. But we can't take the derivative there because it's a sharp corner. So the other thing is just be careful that your limits don't agree. Anyway, we'll leave that there. Okay, this is where things get a little nicer. I'm going to present, I think, 3 or 4 rules here. And after we present them, we're going to assume them and just use them like nothing. We combine these all the time. So once you get these 4 down, a lot of derivatives will be a lot easier. And the next sections, the derivatives we use for that will be nicer too. We'll just use these without thinking about them much. So our first one, let's switch colors. Some blue today. Our constant rule. If our function is a constant, so y equals some value c. We look at the slope of that line, that slope is 0. So the derivative is always 0. There's no change. Like you don't go up, you don't go down, you're just flat. Excuse me. So that's our constant. Constants kind of drop off for us. It's nice. We're just going to leave that one. Power rule. So if we have x to a power, our power comes in front and we subtract 1. Your n is a real number. This works for positives, negatives, fractions, decimals, anything. It's a really awesome rule. So I have a couple examples here. We want to use the power rule, f prime of x. We bring our 4 in front. So this gives me 4x. Now I take my original and subtract 1. So 4 minus 1 is 3. And that's our derivative. That is a very nice rule. For the next one, I have a 3 on the denominator. We can deal with that with a different rule that's coming up, but we can make this a simpler problem too. So I'm going to rewrite this, throw that in black. If we have a exponent on the denominator, we can bring it up, make it negative. So this is going to turn into x to the negative 3. And now I can take the derivative, and it works the same way. Just be careful of your signs. So I bring that in front, negative 3x. Negative 3 minus 1 is negative 4. Be careful there. Don't add instead of subtract. We're still subtracting. Oh, yep, there's my next rule. F prime of x. All right, if we have a fraction, it's the same thing. We bring it in front. I get 1/2 x. 1/2 minus 1 is negative half. I'm going to add 1 in here that I should have written down from the get-go. F of x equals 3x squared. Okay. A lot of times for our derivatives, we want to rewrite our function into a nicer format, and then the derivative becomes fairly straightforward. We don't have to do a lot of mental gymnastics for that. So for this one, I have the cube root of x squared. I chose that because it's got a couple things going on. First thing, a cube root is to the 1/3 power. Now, when we have exponents to an exponent, so x squared to the 1/3, we multiply our exponents. So this gives me x 2 over 1 times 1 over 3 to the 2/3. Cool. So f prime of x, bring this out front, 2/3 x. 2/3 minus 1 is negative 1/3. You'll get really good at subtracting 1 from various numbers. So that one looks complicated, but once you clean it up, it's the same rule. Another thing to note before I forget, a number like this is the same thing these all mean the same thing. You choose your format based on the problem. I can't tell you exactly when you choose one versus the other. It just kind of pops up in different problems, whatever's natural. When we work with it, we want this last format. But just know that those 3 things are equivalent. They mean the same thing. Quick drink. This is the most common one. I almost forget that it's its own rule because I like to throw it in with the other ones. Constant multiple rule. So suppose f is a differentiable function, which is what that nonsense means, and our c is a real number. Then we kind of think of it as pull your c out. So pull it out of the derivative, out of the function. We just get c times f prime of x. So in practice, let's find the derivative of this dude. We think of this as 5. The derivative of x squared is just 2x. which we clean up to 10x. Most of the time, we don't write this, we don't write the middle piece. So we will just skip writing that all together and just go straight to the 10x. I like to add more steps than necessary at first. No, not rainbow. That looks weird. I love rainbows, but it looks weird. Okay. Be cautious of your fractions. So 2 times 1/2. Do a little fraction side work. Equals 1. So I get x to the negative half. Again, fairly straightforward. All right. This is going to rewrite. T is going to work just like x. Note that A, B, C are usually your real numbers. X, Y, T, Z are your variables. I can't tell you that 100% of the time that's the case, but most of the time we save those for variables. H comes over here too. And then F and G are your functions. If that changes in the middle of a problem, I'll let you know, but most of the time that's going to be your rule of thumb. Okay. Now I rewrote my problem. It's a little nicer. I can bring my 2 down. Oh, whoops, that is a thank you Windows. Nobody cares. All right, I'll add an extra step. 2 over 1 times 4 over 5. 2 minus 1 is 1, which gives me 8/5 T. My final answer. Thing to say about that. Oh, that's to the 1 first power. That's why I wrote that. That just looks weird. I'm so in the habit of writing X that I should have written a T here. Sorry. Be careful of your fractions. You're going to want to simplify your final answer. Don't worry about simplifying until you get to the end, unless simplifying would make the numbers nicer to deal with. I try to avoid fractions in the middle of my problem because they make them messy, but sometimes you have to. All right, the last rule is our sum and difference rule. This works exactly like you want it to work. So if you have 2 functions and you're adding them or subtracting them, it's the same thing. We can just take the derivative of each part. Honestly, we get so used to this rule, we don't think about it either. We just kind of becomes natural. I promise these things get easier. All right. I have x to the 4th and negative 2x. So I'm subtracting 2 functions. I take the derivative separately. So the derivative of x to the 4th is 4x cubed. The derivative of negative 2x is just negative 2. I should have added some different. I'm going to add one more at the end here because I think it'll be a little easier, or something we need to talk about. So straightforward. This next one, we don't know how to deal with a function like this yet, but we don't have to in the format it is. We can manipulate. You always want to simplify as much as you can before you deal with your problem. Okay, this is better. We're getting there. I'm going to turn these all into simpler terms. X cubed over x, x squared, 5x over x. Oh, this will illustrate my point. X. And here I'm going to bring it up so it's still a negative on the outside to the negative first. As always, watch your signs. All right, so that was just the side work. All right, derivative of x squared. I bring my 2 out in front, 2x. Derivative of 5 is 0. We haven't used the constant rule, but don't forget that. Derivative of negative x to the negative first. So negative times negative 1 gives me positive 1 x to the negative 2. That looks really gross. I don't like that. Clean it up a little bit. 2x plus x to the negative 2. I am 100% happy with that. I would leave that. If homework makes you simplify it a little more, we can. So my plus 1 over x squared. Common denominator. So multiply this one by x squared over x squared. 2x cubed plus 1 over x squared. Honestly, I like this one better, but this is also an answer. I'm going to throw one more at you. Okay, this one illustrates all of our rules together that I can think of. I'm going to clean up one step. We'll go this direction. So 3x to the half plus 7x minus x to the negative 2 plus 9. Now it's in a format we can deal with a little easier. So challenge, can you beat me to the final answer? Can you do this without me? Pause the video if you want. All right, bring this down. 3 times 1/2 is 3 halves. That looks a little weird, whatever. X, subtract 1, so 1/2 minus 1 is negative half. Plus, this is the first, 7 times 1 is 7. We get x to the 1 minus 1, or x to the 0, which is just 1. The x goes away. So let's note that ax, the derivative of that is just a. All right, negative times negative 2 gives me a positive 2x, come on, pen, to the negative 3 because we subtract 1. And then the derivative of a constant is 0. So my final answer is right there. Okay. That is it for this one. The next sections I think are applications, so I might just write notes and not do a video. I haven't really decided. You're using some of these things, which most of the time it walks you through that. I'm more focused on the derivative rules than the application of explaining it, just because those are a little more challenging. All right, this video is at 40 minutes, so I'm going to call it there, and I will see you next time.